What's up, everyone? It's calc time, the time you've been waiting for. I'm Miss Wesley, and I'm excited to get started with you at the top of page 11 in Differentiation Packet 2, where it says tougher chain rule problems. Really, we're picking things back up right where we left off last class, but now knowing that we have about 4 or so rules that are shortcuts in terms of taking derivatives. So after we learned the definition of derivative was the time we got the power rule, which is pretty convenient for finding derivatives of terms of polynomials. After that, we proceeded to get the product rule, right? In the case of a product, quotient rule came after that. And the most recently added rule to the list, the chain rule, one of my personal faves. But although the page says tougher problems, don't let that scare you off. These problems aren't necessarily more difficult to differentiate. It's just that you have to think critically about which rule to use when in order to be able to solve these. So we're going to make some of those decisions together as a class as we practice today. I think a good idea would be to warm up with these top 2 questions, or maybe just this first one on page 11. I'd also like to start things off with a joke. So here's your joke. Why were the I and the V and the X always wandering around? Well, that's because they're the roaming numerals, you might say. Let's give this one a shot. And I want to refresh what we were talking about with chain rule the other day. The chain rule is convenient when you don't feel like foiling this thing out and really raising it to the 50th power expanded. The chain rule comes in handy when you have these what I call outside and inside portions of the function. And by the outermost portion of the function, I'm talking about that 50th power. This is your main event, that you're raising everything to the 50th, and that is your first order of business when you're going to take a derivative. Deal with the 50 first using the power rule. Swing down the 50. Rewrite the inside of parentheses. This doesn't change just yet. 3x minus 2x squared. And now because you're using the power rule, this thing ends up being raised to the 49th power, right? One lower than your original. I could check off the 50th power now. We've dealt with that, but we still have to go inside, and we're going to chain on the derivative of the innermost part of the function. And this can go in parentheses. So derivative of 3x, a 3, minus the derivative of 2x squared, so 4x. We'll leave it like that. Take a look. The good thing about these videos is you're able to pause and rewind if we go through anything too quickly, and I would invite all the questions that you guys might have about this. But what I like about chain rule is I deal with each part and I'm done with it. There's no fancy real pattern to memorize, and it's called the chain rule like we said because each part of the derivative is tagged on with multiplication. I think the challenge is going to become, as I scroll down the page and look at 4, 5, 6, and 7, I can't guarantee that you're just using one rule when you're trying to find the derivative of these things. There are many times where you might be using, I don't know, some kind of quotient rule in this one, but a chain within that quotient rule. So now's a good time to practice. Let's see if we can mix things up a little bit and let's start with number 4. So for 4, I think the one cool thing about the problem is we might be able to make it look a little bit easier off the bat because it's just a constant in the numerator. Initially, I was thinking this might be a good quotient rule example, but since there's just a -7 up top, let's swing up the denominator. Let's take the original f of t and rewrite it as -7. Now we're swinging up what's in the bottom, and once it gets swung up, it's raised to the -2, and that would be a 2t minus 3. So we haven't started taking a derivative yet. We'll do that next, f prime of t. We're just rewriting the original so that now we actually don't have to use quotient rule. We can just chain rule to solve this problem. Okay, so that's the next step, is we're going to try to use chain rule to take a derivative here. So why do I say chain rule? Let's see. Okay, well, I know that I don't really need a product rule despite the fact that this is a product because the coefficient sitting out front doesn't have any variable with it. It's just a plain old -7 that can get transferred to our solution. Then I look at this and it reminds me of the warm-up example. We deal with the outermost portion of the function first, right? Here comes the chain rule, the -2. Let's do that by swinging down a -2 and raising what was inside of the parentheses to 1 power lower, the -3rd power. So let's put a 2t minus 3 in there. So that gets checked off. Now we still have this to deal with. The 2t minus 3 needs to be handled. So we're going to tag on by chain rule with multiplication an innermost derivative, which in this case is just the number 2. And here's what I was talking about before. Maybe we reorder things. We can clearly, within 20 seconds, just multiply these three constants, right? A negative 7 times a negative 2 times a 2 to get the number 28. So I like the final answer having a positive 28 out front, 2t minus 3 to the negative third power. And this is a great way to leave it. Okay, so a chain rule that we made a quotient into, we gave ourselves a situation where you could just chain it. All right, let's try a couple more. 5. 5 looks like it'll have a chain rule aspect to it. We'll see a function that's got a square root around an innermost part of that function. But look, you've also got, can you write PR here? You've also got a product rule to deal with. This could be your f function, and this could be your g function. So this is going to be one of the trickier problems we've ever done as of yet. But let's give this a try. We'll call the whole thing f prime of x. We're taking a derivative. And I want to think of a product rule that I could use for this. So here's f, and here's g. We need f prime g. Try that first. So f prime, the derivative of x squared, is going to be 2x. Next to it, let's write g normal, so it'll be the square root. So square root of 1 minus x squared. And this is half of the product rule. We've got f prime, and we've got g. All right, now the tougher part, g prime f. Well, I'm going to write f out of order here just so that I don't forget about it. Here's regular, the first part of the function. And now for the part that we have to be a little bit more careful with. This is a good chain rule situation. Consider it 1 minus x squared. If you think of the square root as a power, we could use the 1/2 power to denote a square root. And now I know main event, outermost portion of the function, like these other questions, is going to be that 1/2 power. Let's deal with it first. We'll swing it down front, swing down the 1/2. Raise 1 minus x to 1 degree lower than 1/2, so negative 1/2. And then we got to remember to tag on an innermost derivative. So at this point, right, the 1/2 is checked off. Now I have to go into the parentheses and see if I have any interesting derivative in there. And to check this off, I think I just write a negative 1. The derivative of the inside, 1 minus x. So take a look at it. This last part is all g prime. That last part was a little sneaky chain rule inside of a product rule. There's not much I would do to simplify. I would leave the whole first half of this as is. And then afterwards, what? This whole thing will come out to be negative 1 times 1/2, so negative 1/2. How about x squared? And then multiply that by 1 minus x to the negative 1/2. So it takes a little bit longer than your normal question, but it's a great review problem, right? When you see a chain rule mixed in together in the midst of a product. All right, what about a quotient? You knew these were coming, 6 and 7. So for 6, man, it was kind of nice in number 5, or number 4, I should say, how we were able to just swing up the denominator and proceed from there, bypassing the quotient rule. But I think at this point, if you have any kind of variable expression on top and bottom, like I see in number 6 and 7, I think it's in your best interest to do a quotient rule for this question. So we're going to try this one. I'll put QR. And try this one carefully and slowly together by quotient rule. All right, so f prime of x. Here goes. Let's leave a lot of room for a numerator and denominator, and let's work on f prime g, the first part of the quotient rule. So derivative of the top, the derivative of x is just the number 1. Don't even really need to leave anything there. Multiply that by g, which is the bottom, through the cube root of x squared plus 4. And then I have to think back to quotient rule. Quotient rule has a minus sign right in the middle of the numerator. And we're going to reverse what we just did. We need derivative of the bottom times the top. Let me write the numerator normal just so I don't forget about it. The top normal. And now let's work on chain ruling the bottom. And I want to think, just like we did in the last one, I want to think of the bottom as x squared plus 4, right? That was inside a cube root. That's like saying the whole thing is raised to the 1/3 power. And here goes the chain rule, right? First deal with the 1/3. So 1/3 times x squared plus 4 to 1 power lower. So 1/3 minus 1 gives me negative 2/3. And then lastly, now let's check off the inside. The x squared plus 4 needs to be differentiated. So we'll take a derivative of x squared plus 4 and just write 2x. So all that is involved. Everything in blue here basically is the derivative of the bottom. And then we have the top there normal. We get a little bit of relief in the denominator. We just have to take the current denominator, the cube root of x squared plus 4, and square it. We'll talk about whether or not we want to write this in a different way later, but for now, that's a good way to leave the bottom. In terms of simplifying, there's not much we're going to do. I think we're going to multiply the x times 1/3 by the 2x here. So you'll have just this as your first part, cube root of x squared plus 4. Then we'll say minus 2/3 of x times x, so 2/3 x squared. And I'm going to leave this as a power as well, x squared plus 4 to the negative 3/2, or negative 2/3, I should say. All over. Feel free if you want to leave this way, that's fine. Or you can write it as a fractional power. That works too. X squared plus 4 to the 2/3 is an okay way to leave it. And I'm going to admit here, there is more simplifying we could do, but we're 22nd ruling it at this point. I know that we could simplify and probably figure out a power of each of these to reduce this by, but I don't think it's that important at this moment. I think the biggest part of this was this crazy section here where we took a derivative of the bottom using chain rule within this quotient. Okay, so then when you get to 7, I want to circle this one too, you get to a spot another time where you have a choice of which method you want to use for starters. It says you've got a whole fraction raised to the second power. And one thing that you might want to do that some people do is they bring the power into both parts, right? They'll raise the top to the second power and the bottom separately to the second power. I think we chain rule with the 2 first, and we have a quotient rule within it when we go to differentiate the innermost portion of the function. So my advice is for g prime of x, let's handle the outermost portion of the function first. Let's handle the second power. So swing it down. We'll make it 2 times this same fraction, 3x minus 1 over x squared plus 3. Whoops. To what power? To the 1. It's going to be 1 power lower. And we can check off the 2 as being handled. Now we've got to go inside and not forget to quotient rule the stuff that we have written in here. So that would require one big fraction. Okay, so here goes nothing. We've got to do f prime g minus g prime f if we think back to quotient rule. So quotient rule says take derivative of the top. I think it's just going to be the number 3. Multiply it by the bottom, x squared plus 3. See how that looks. Okay, so I think that's it for f prime, top derivative, times bottom, g. Minus, since it's a quotient rule, and now it's time to write g prime f. So derivative of the bottom, 2x times the normal numerator, 3x minus 1. See if that looks okay for g prime and then f, derivative of, or regular numerator. On the bottom, we just get to write the existing denominator squared, which is nice. So x squared plus 3, and then that thing is squared. Truthfully, we've got all the parts we need. We have a good working derivative at this point, but if you're able to simplify a few things, and as long as we're talking together, we might as well. Let's give this a try. What do we have? I guess we could simplify the top here. So maybe we'll make this all one big fraction over the third power of this binomial. Here's one of them, here's 2 more. So we can make the total denominator x squared plus 3 to the third. What else? Up top, you've got 2. You've got 3x minus 1, and then you have something that I said we could clean up a little bit. So here comes the 3 distributed into the x squared plus 3, so 3x squared plus 9, and then minus 6x squared, now being really careful with signs, plus 2x. At this point, I'll simplify a tad more, and I'll just work on this inner part of those parentheses. So I'll have a 2, a 3x minus 1, and then what? Negative 3x squared plus 2x, I think plus 9. And then denominator is going to stay the same. See how this looks? I think this was just valuable time to practice with a mixture of the different rules. This should also be the third power. But I'm going to circle this solution and know that even our first version of that solution was pretty good because we had everything in the right spots. Okay, I can't wait to hear what questions you have and get more of a chance to practice with these rules in the coming days. I will talk to you soon. Have a great day.